Hello. This is the problem solution session for Chapter 9, Current and Resistance. And the first problem is this. An electrical current is given by the expression of this current. And the question is, what is the total charge by the current from given time period? Okay. So in order to solve this, we have to think about how the charge and the current is related. So we have a dq over dt is it. And then from this, we can get q is given by this one. And then we are given current. And we have two time periods. T0 is 0, and T1 is this one. And then we can set up the integral like this. Okay. And then we get the integral. The sign becomes minus cosine. And then this integral will turn into these equations. And then if you just apply this time, and then you will get the final result is this. So if you take care of this numerical calculation, you will get the answers. Okay, so the quantity of charge in a coulomb passing through a surface area of 2.4 square centimeters. And then it varies with the time, such that right now is Qt is given. Note the previous case, IT is given. Now we have a Qt is given. And obviously, for the given Qt, we need to find out the current density. So it's not just simple current, it is a current density. J is given by I cross-sectional area. So do we have information on the cross-sectional area? Yes, we do. So here is this one. So first thing is that we set it up, the Qt, the charge, as a function of time, and surface area is given like this. And then from the Qt, we can find out current. Okay, and then as a result, if you take a derivative of this one, then you get this one. Okay, and then and we need to careful about those units once again. If it is coulomb, then we need to change to the meter square. Coulomb goes with the meter square, not the centimeter square, so that our area is now changed into this number with this unit, meter square. And then current density is given by, J is given by I cross area. Okay, so we have a 12 ampere. At t equal to 1, note that t equal to 1, if you just plug in t equal to 1, you get 12 ampere. That's the value we need to plug in, because the problem says that what is the value of the current density at t equal to 1 second? So this value should be used for our calculations. And then we get the current density. So this problem is we need to understand the relationship between charge and current. And then we need to also understand the relationship between charge density and current density and the current, okay? So we know that I is given by dqdt, this relationship, and this relationship. Okay, now let's move on to the next one. Aluminum wire with this diameter carries a current of 4 ampere. What is the drift velocity of electrons? So now we have a different aspect of the current. So all of this is related with the current. And now it is previous cases we were dealing with the cases where the charge uh, is given as a function of time so that we can take the derivative to get the current. But in this case, we are given different informations, such as aluminum density, mass density, molar mass of aluminum, and there is Avogadro number, and the elemental charge is given by this. So that the previous two problems and this problem is quite different because the information is different and the question is also different, drift velocity. Okay, so you need to understand how the drift velocity is derived and what are the related formulae. So in this case, our current is related with the drift velocity like this, and such that our drift velocity can be found for a given current, and this N, E, and A. Here, N is, note that is the number density of free electrons, number per cubic meter. A is the cross-sectional area of the wire. So let's try to find out one by one. So cross-sectional area of the wire, A, is given by pi r square, and r is given by this one, which is the diameter divided by the 2, and then we can get the pi r square, and then it is given by meter square. Okay, so this is the A we want to have. And then what about the electron number density? This is the core of this problem. So what are the what informations are given? So that if you look at it, we want to find out the number density, not the mass density. So how do we find out the atomic number density? Number density from the given informations. So we have a law, the mass density, and this is the molar mass, and Na is Avogadro number. Avogadro number, which is, as you can see, this number, 6 times 10 to the 23. Okay. And then in this case, you can get the number density in these ways. Okay. So if you just plug in those law, this one, and the molar mass, M, this one, then you'll get the law of M is given by this one. And then if you just plug in Avogadro number on the top of it, and then you will get these atoms per meter square. And then what is important in this case is the number density of electrons. So if we assume that there's only contribute on one conduction electron per atom, then you get these electrons per meter cubic meter. So this number, step 2 is important. So from the given information, the aluminum density and the molar mass, and we need to find out the electron number density. Okay. And then if we know the area and number density, and we know what the electron charge is, number density, area, and the current is given, right? And then you can find out drip velocity. So we get the drip velocity is given by this formula, and then you get drip velocity is order over 10 to the minus 4 meter per second. That means drip velocity of electrons in a conductor is pretty slow, 10 to the 4 meter per second. Okay. What current flows through the 2.54 centimeter diameter rod over pure silicon that is 20 centimeter long? Okay. When a certain voltage is applied to it, and remember that the condition is resistivity of silicon is given by this number. Okay. Note that the unit ohm times meter. Okay. So let's try to find out what is important to get it. So the question is the current. Okay, question is the current, and the given conditions are structural parameter of aluminum rod. So that we have this parameter D is given, L is given, and it is connected to a certain voltage. Okay, and then it is the volt. So basically we have V. And then if we identify what the resistance is for a given voltage, we know that current is given by, okay, that is the thing we need to have. And let's try to find out what the resistance is. R is given by resistivity times length over area. Okay, the cross-sectional area is given by, in this case, is pi r square, where R is d over 2, and L is also given. And it is important to have all the units in the meter. Okay, A is given like this, and then it is given by this meter square. And then resistance is given by rho times, rho is the resistivity, L over A. So note that rho is given by here, 2,300 ohm times meter. So there's a ohm times meter. Length is given by meter, area is given by meter square. Then we get, this is cancelled out, it is ohm. Okay, so that we have this ohm. Now we know the resistivity and we know the voltage. Then I is given by voltage over resistance. And then we get this much over current in ampere. So once again, I'm just emphasizing you that you need to keep the unit consistent. It should be all meter, and it should be all in coulomb, or it should be all in volt, etc. Okay. Now, let's try to think about a coaxial cable. Coaxial cable is a very important element in the electronics. Okay, so in this case, we have seen this coaxial cable has a capacitor, and it also carries resistance, and it also carries inductance. So within this single element, we have a both capacitor, resistor, and inductor, CRL, all together. But we are going to concern about the resistance. Okay. So calculate the resistance of the silicon between the two conductors. This is the silicon. Resistance, a silicon layer has this resistivity. Okay. So what is happening here is that from the center conductor to outer conductor, there is a current. Current is flowing. Okay. This is the very important setting. Okay. So if you think that current is flowing this direction, then you are getting the problem wrong. So as it says, that there's a radial direction. There's a flow of a current. Okay, so that is an important setting. We want the radial resistance of a silicon annulus between the two coaxial cable cylindrical conductors. Inner radius of A and the outer radius of B. Current leaks radially through the silicon from the inner conductor to the outer conductor. That is the scheme. So let's try to find out what is going to happen for the at radius of R. Okay, let's assume that this is R. R. And then we are looking at the uh, cylindrical structure. Just look at this blue element, and that this is R, and this is the dr. Okay. So area is, in this case, is the area is circumference times the length is 2 pi r times L. 2 pi r is the circumference of the circle. And then there is a L. Okay. A thin radial slice of a thickness dr has a resistance. Okay, so dr is given by rho dr over ar. Okay, so that is the important one. dr is, note that this is the nothing but r is given by rho times l times a, right? So here's a. Length in this case is, in fact, this is the radial distance from here to here. Okay. Uh, don't get it wrong here. So that what is important thing is that this one, so that it serves as a whole area, and then there is a dr as a length. This is a little bit different from what we have seen before. So we have a certain area and then length. But in this case, we have a area is, this is the area, and the length is dr. The reason why is that the current is flowing radially. In this case, current is flowing in these directions. So it is different geometry. You need to understand this. This formula is very important. Okay, this is the radial resistance for radial current. Okay, the current is flowing from here to radially flowing. Okay, so if we understand this formula, next thing is, so we integrated the total resistance, which is starting from A to B for dr. And then you see that it is given by this one, which is, we have already studied a formula in our classes. But anyway, we are deriving the formula once again. And then we are going to convert all dimensions into SI units so that everything is changed into meter. And then plug in numbers. As A and B is given in meter, and then the L is given in the meter, and then R is given this one. Okay. So key point is this one. So you need to know the current is flowing radially from A to B, and then we need to understand that resistance is given by this one, but in this case, A is the side area of a cylinder, and L is the infinitesimal distance, okay, where the current is flowing, okay. Note that in the case of this kind of a conventional resistance, note that the length was parallel to the where the currents are flowing. So in this case, currents are flowing in the radial direction, so that dr is the length that is related with the resistivity here. So you need to have dr, and that this is a side surface area of a cylinder. Okay, that is the key thing. And now let's try to think about another one. In a certain particle accelerator, electrons emerge with energy. The electrons emerges not in a steady, but rather in a pulse. And the pulse rate is given by this number, 150 pulses per second. This is per second. This corresponds to the time between the pulses of this t and the delta t. Okay. And what is the maximum power delivered by this electrons beam? So within these pulses, there are electrons. Electrons, 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 electrons. And then we want to find out the maximum power of these electron beams. So power from the particle beam, we need to consider energy delivered divided by the time. And then if each electron has an energy E and the beam delivers n electrons per second. The reason why we are talking about per second is that this pulses per second. per second is given, so that we have the time dimension here. And if you know the n electrons per second is given for the energy, then power is given by n times E. So now it's time to think about how to change the energy. The energy is given by 2.25 mega electron volt. Mega means 10 to the 6 electron volt is given. Electron volt can be converted into joules with this conversion factor, such that we have an energy in terms of a joule. Okay, and now it's time to think about how to find out the n electrons per second. Okay, it's easy if you call back what is the relationship between the current and charges. So you have a current is given by dq over dt. So each electron has a charge E. The number of electrons per second is given by here, this one. Okay. I is as a charge over second, or coulomb or second. And then the number of electrons per second is given by charge divided by the electron. If you have the current is charge per second, if you divide by the electron charge, then it becomes a number. Okay. So during the pulse, we have Imax is this current, and then if you divide it by our electron charges, then that is the n electrons per electron numbers per second. And then we have all the information available. So Pmax is given by n times E. So n is known and E is known. And then if you multiply by this one, note that is given by the joule and is per second inverse. And joule divided by second is watt. Okay, that's the thing we need to keep in mind. And now it's time to think about another problem. Find the ratio of power delivered to 16 identical resistors in series to the power delivered to the same resistors in parallel configuration. So that we have a two configuration. One is 16 resistors are connected in series. The other configuration is 16 resistors are connected in parallel. And the voltage is given as given as 0.8 volt. So the power has to be figured out. In this case, we note that the voltage is given, and somehow we have all resistance also given. And for the given voltage and the given resistance, we can calculate the power. But in this case, voltage should be volt, and resistance should be in the ohm. Okay. Okay, so equivalent resistance 16 series. We know that in the series it is just a simple addition, so it is 16R. So in this case, power is given by this one. And what about the equivalent resistance in 16 parallel? Then we get this formula. Remember that. Sixteen. Okay, so we have our parallel is given by all over 16, so that in this case, our parallel is given by this formula. So ratio over power is given by this one, so series over parallel is 1 over 256. That means uh, the series connection of the resistance will have a lower power than the parallel configurations. 19, electron beam emerging from a certain high energy electron accelerator has a circular cross-section of radius of 1.1 millimeter. And the speed of the electrons is so close to the speed of the light that had the speed light, and it is about this value. If the beam current is this one, what is the electron density of the beam? So now we have a different entity here. So it is the electron beam, and then if the beam current is the 5 micron, and we need to find out how many electrons per cubic meters are in present of this electron beam. Once again, we need to understand I is given by, current is given by dq over dt, okay? And the beam with the number density over n, that's what we want to find out, with the cross-sectional area over A and the speed over B. And it is dq over dt is number of electrons times electron charge. And then you have an area times V. So note that it is given by L square, length square times length over second time. And then this is 1 over length cubic. Then this will cancel out such that you will have a coulomb, you have an electron charge, coulomb per second. It is ampere, okay? So if you do not remember the formula, then you have to do the dimensional analysis, which we have learned in the physics 161, which is very important. So the current is related to the number density that we want to find out. So that our number density is given by I divided by the ABE. So if you look at closely, then you'll see that the cross-sectional area is given, velocity is given. So cross-sectional A is given, right? So A is given in terms of meter square. And then the velocity is also given, which is the light velocity. So B is this one. A is this one. And we know what the charges are. And then we have a current, right? Beam current is given by this 5 microampere. So it is 10 to the minus 6 ampere. So everything should be in a proper unit, okay? And then you can get the number density. So now the next problem, a metal wire of resistance R is lengthened 3.5 times its original length by being pulled through a small hole. So basically we have a small hole By passing through a small hole, we increase the length. Okay. So we note that the resistance is given by this basic formula. And one initially has a cross-sectional area is A0, and then there is a L0, and now it's changed to A1 with the L1. Okay? So that's the situation. That means the material property, rho, did not change at all, but its structural parameters, length and area, is changed. And how they change it, remember that the volume conservation or mass conservation, so initial volume should be the same as the final volume. And volume is given by area times the length. And then, so we have A0, L0 should be the initial and final. Such that, and then we note that L1 is lengthened by the 3.5 times. Okay. And then A1 is given by this one, and then you have a area should be reduced, right? Just look at this. If the length is increased, the area should be reduced. And then original resistance is given by this one, and the final resistance is this one. And then R1 is given by this value, okay? A high voltage transmission line with a diameter of 2.2 centimeters and length of 180 kilometer carries a current this much. And if the conductor is a wire with a free charge density of this electron density, how long does it take? How long does it take? One electron traveled the full length of a cable, okay? So it is, we want the time of one electron to drift the full cable length. So electrons moves with a drift speed, okay? This is the thing we need to find out, okay? Drift velocity. So let's try to find out what we have. So we have a diameter, so that we have a radius. This will give us an area, the length is given, and the current is given. And we have a free electron number density is given, and is given. And the elemental charge is given like this. And then from this information, what can we get? So for a conductor with a mobile charge carries, current is given by NEABD. That's it. And then drift velocity is given by I over NEB. Okay. So we have all the information, such as at this moment. We know what the I's are. We know what the area is. We know what the E is. We know what the N is. But the thing is that we have to do it carefully such that the area should be meter square. And then all the things should be in the meter per second, etc. And then if you just plug in all the appropriate numbers with the correct units, and then you'll get drift velocity in terms of meter per second. Okay, so that's it. And then once velocity is given, drift velocity is given, then what we need to do is to try to find out drift time. The the length, so we have a length is given. And then each electron travels with the drift velocity. And then the time it takes from here to here will be distance divided by the velocity. Okay? In other words, Vd t is going to be L. So time is going to be obtained by this formula, and then you will get this second. Okay? That's the answer. Because the drift velocity is fairly slow, so the time it takes to travel this length is quite long, 10 to the 8 seconds, which is very long. So you can get the scale, what is going on in just a coaxial cable. Okay, that's it. And then I hope you understand the basic concept of the current in a conducting wire. Thank you.